think we have started recording. Yes. Okay, so let's get started. So we are going to be talking about defenses today and for the next few weeks. So let us start with an overview of what we have covered so far in terms of defenses. So we have looked at stack canaries. We have looked at W XOR X, and we have looked at ASLR. So ASLR and W XOR X were both operating system level defenses, in the sense that you could take an existing legacy program compiled already, you just have the executable code, and then you drop it into the system where you have ASLR or W XOR X enabled, and the defense just works out of the box, right? The reason is because both ASLR as well as W XOR X work at the level of the process page layout, and so there is nothing in the code that needs to change in order for these defenses to work. In order to enable stack canaries, however, we required some support in terms of inserting these canaries, checking the canaries, and so on. And there are various ways to do it. One way that we saw was where the compiler inserted instrumentation into the generated code. Okay, so these are 2 points in the design space. So as it is, you can see, in terms of the design space, one does not require access to source code, one did require access to source code. So you can see how we have covered 2 points in the design space. It's also interesting to see what kind of attacks they can prevent, right? So address space layout randomization gives you a probabilistic guarantee of security, in the sense that it says, look, at an attack that worked in one layout is likely not to work in the other layout. It may end up corrupting your stack because a buffer overflow may not be successful, but you might end up corrupting other elements in the stack. And it also has the side effect of converting a buffer overflow exploit into a program termination, probably using a segmentation fault. Same thing with W XOR X, right? You had a problem, it would try to stop the program from executing the injected code. Of course, it cannot defend against code reuse attacks such as return-oriented programming. Right? So we sort of established the power as well as the weakness of that solution. We also saw, what are the weaknesses of stack canaries, weaknesses and strength of stack canaries. The weakness, of course, is that it's not a perfect defense. It only protects return addresses and probably function pointers based upon where you place the canary. It does not protect other local variables that are placed in the stack. It does not, it does require access to source code, and it does place a performance penalty, right? So these are like the ways in which we can summarize the defenses that we already know. So today, let us talk about another important class of defenses, which is that of bounce checking. Okay, so in order to understand bounce checking, let us go and understand what Java does in order to prevent things like buffer overflows. So if any of you has programmed with Java and you have created an array and you try to write past the end of the array, you see that you get an exception, a runtime exception. Okay, so clearly Java is doing something at runtime, that is checking whether you are writing into the array properly, and if you're trying to exceed the bounds of the array, it is going to throw an exception. So how is this bounce checking implemented, right? So any ideas how these how Java does this? Please, you can feel free to raise your hand. How do you think Java goes about performing these checks? Nobody? Yes, Shashank, please go ahead.
Sir, it must contain extra information related to bounds so that it can check whether the address that we are trying to dereference or we are trying to access, whether it is in the bounds of the current object or not.
Okay, very good. Okay, so you mentioned this word extra information, and I'm going to use a particular term to refer to this extra information. This is going to be called metadata. Okay, we are going to be calling this security metadata, bounce checking metadata, whatever it is. This extra information that you use in order to determine whether a write into a buffer is within the bounds or not, is we are going to be referring to that using a term called metadata. And in particular, we are going to be talking about one approach to bounce checking, which is called fat pointers. Okay, and so the general goal behind this approach asks the following question: can we take a language like C or C++ and provide C or C++ with Java-like memory safety in the sense of performing these checks, these bounce checks at runtime? So let us try to understand, what are the difficulties in doing so in a language such as C. And so let me just show you some code, right? We are going to do this interactively. By the way, I realized that one of the problems that the reason why I was not able to write last time is that my stylus apparently uses a special battery size, which I could not find in any shop. So I have ordered it. So next class onwards, hopefully you should be able to see me writing something on Jamboard. But for today, you will have to bear with me as I try to figure out how to write these things on slides. Okay, so all right, so let us take let us take the following program. Okay, it's a simple C program. Okay, I do a char star P, and maybe I do a malloc of this P somewhere. It doesn't matter how much size I allocate for it. Or it could be a stack buffer, doesn't matter. And then I do a stir copy into this P from some source buffer. Okay, so we saw that this is potentially a problem, and the reason it's a problem is because stir copy does not do any bounce checks, right? But let us say that we had a version of stir copy, and I'm going to call that stir copy safe, that is capable of doing bounce checks. Okay, the question is, how do you even enable these kinds of bounce checks on this stir copy safe when you're just passing it two pointers? You're passing it a pointer P and a pointer to this some source buffer, but you're not passing any bounce information. You do not know how long this buffer P is supposed to be. So how do you even initialize the checking of this, right? Of course, there's a stir copy safe, which is stir M copy and or stir L copy, but there you actually take the size of the number of bytes that you want to copy to P. I'm not going to do that. I'm not going to change that. I'm just going to take stir copy, and then I'm going to say, look, pretty much the same API, but I want to be able to now determine whether the thing is within bounds or not. Okay, so how do I go about doing this? The problem is in C I cannot do it. The reason I cannot do it is because okay, looks like there is some problem with Teams. There are some people who are on the chat window. Is there some sort of a delay in the voice coming through?
Sir, the voice is not having a delay. The video is having a delay.
The video is having a delay. Okay, okay.
Yes.
All right. I don't know how to resolve it. I'm sitting in the best network possible, which is the department network.
Now it seems to be all right, sir. It was worse a minute before. Now it seems to be all right.
Okay, okay, okay. All right. All right. Okay, so let's hope it resolves itself over time. All right. So the problem is that there is no bounce information. Okay. So I'm going to give you one possible idea to pass this bounce information, which is that every pointer, for example, this character pointer, I'm going to convert it into a struct, right? I'm going to convert it into a struct called a struct fat char pointer, okay, which is going to be the following, right? So it's going to contain three fields. The first field is, of course, the char pointer itself, and I'm going to call that pointer, the actual value of the pointer, and it's going to have a it doesn't even matter if it's a char or a I can even make it a void, which is the base, and I'm going to pass another pointer called the bound. Okay. This bound, I'll tell you the meaning of these pointers in just a second, but the idea is this could also be an integer. It doesn't matter, and I will tell you based upon the interpretation. Okay, so I'm going to convert every pointer into this new structure called fat char pointer, which consists of the original value of the pointer, which is denoted by this char pointer, as well as two pieces of extra information. Okay, which is the base and the bound. The base is the original value of the pointer at which, let's say, the malloc returns the pointer base, or it could be, if it's a stack allocated pointer, it could be the starting address of the buffer, and the bound will be the last legal address of the buffer, which is that, if it is, let's say you do a malloc of size 24, this bound will be base plus 24. Okay, so that is the last valid pointer corresponding to this particular buffer. That's why you see, you can even treat it as an integer if it is instead of a pointer value, instead of the base pointer and the base plus 24, I can just store the base pointer at 24. It depends upon how you do the checking later on, which I'm going to talk about. Okay. So, but abstractly, you have the pointer as well as these two pieces of information. These two pieces of information are the metadata. Okay, so now I'm going to take my program and let us say that I have somehow got a method to convert every pointer into its corresponding fat pointer. There is going to be a fat integer pointer, a fat struct pointer, whatever it is, right? I've got a fat pointer and every pointer has a corresponding base and bounds information. Now, if I have this information, all I need to do is that I need to insert some additional checks into the program. At least now I have the ability to perform the checks because I'm carrying with me, with the pointer, all of the additional information that I need to perform the checks. All I need to do when I'm dereferencing the pointer and writing to it is that I need to check that write into this pointer whenever there is a write that happens into this pointer, that the write happen, that the pointer is pointing between the base and the bounds, that it is not on the left hand side of the base or on the right hand side of the bounds. Okay, if I'm able to do that, then I will be able to prevent buffer overflow bugs completely, buffer overflow exploits completely, because there is no way that the write will be able to violate the bounds of the pointer to begin with. Okay, so that particular concept is called a fat pointer. Okay, a fat pointer is a way of storing additional security metadata, and in this particular case the additional security metadata is the base and the bounds, and I'm going to show you two additional kinds of security metadata, not just base and bounds, that allow you to perform certain kinds of checks on pointers so as to be able to run these Java-like checks whenever you're writing into the into that array. Okay, so what I will be telling you in the rest of today's presentation is, where do you store this metadata, right? So as I have shown you over here, one way to store the metadata is as a struct, right? But you will see that there is an obvious shortcoming to this, which is that stir copy, if you look at the declaration of stir copy takes two character pointers as the arguments, right? So that's the prototype definition of stir copy. I am taking two character pointers. Now, if I change character pointers to a struct, all of a sudden I have broken my program because it no longer works with these kind of libraries. And so I have to recursively change every library that the program is using, and that makes the approach impractical very, very soon, right? So what I'm going to show you is a way by which we can store this metadata information and yet keep it compatible with legacy programs, okay, of this sort, where it still works with libraries of this sort, even if the approach probably does not do the checks always. Okay, so I'll show you that. I'm going to show you one particular implementation of this, which is a compiler-based approach, where you build a special compiler that is going to insert these runtime checks of the base and the bounds. And then I will tell you about Intellibx, which is a processor extension now available on all Intel processors that includes instructions to perform bounds checks. This was introduced in 2013, and I believe it may still be there, although because of whatever reason they are discontinuing it on certain modern chips from Intel. And the power of the fat pointer approach, in the sense that it can completely eliminate any buffer overflows from even happening, right? So it is probably going to be the most powerful approach that we have seen among the kinds of defenses that we have seen. It's more powerful than canaries because it does not just check return addresses, it completely prevents memory safety errors from happening. It is not going to rely on operating system level defenses like ASLR or WXORX, because at the language level, it is enforcing the semantics of C, not semantics of C, rather, the semantics of C are rather loose. It is enforcing a Java-like semantics on C and making sure that you're performing bounce checks at runtime. Okay. I will show you the software approach as well as the hardware approach, and we will sort of cover the pros and the cons of each. All right, so let me start the presentation. So the paper that I'm going to cover is called Softbound although and the presentation itself and the class itself will cover an extension of softbound, which is called softbound sets, which does both spatial as well as temporal checks for memory safety. Okay, and these slides are courtesy of a former colleague of mine, Santosh Nagarkate, and you should Google his name. He's actually an alumnus of the CSA department over here. He was Professor Govindarajan's student in 2005 to 2007, right? And this paper that he has written is really a seminal paper. You should go and read it. It's extremely influential, and it's very, very clean and elegant in its design. Okay, but I must also say that the idea behind fat pointers, this fat pointer based approach, is not something that this particular paper invented. The idea behind fat pointers goes back to a paper from 1993. So 1993 or 1994, I think, was when the idea was first proposed. After that, it kind of died out when in 2002, it sort of saw a resurgence once again when people started looking at how to make C programs much more safe. And 2009, this particular paper that we are going to cover today was published, and in 2013, Intel came up with the Intel MPX. Okay, so you can see that there is nearly a 20-year gap between the time that an idea was first proposed to the time that the idea was actually implemented in hardware with corresponding support in the compiler and so on. So that is, it's not unusual. Sometimes you see a quicker turnaround time from the time that the idea was first proposed to the time that things see their, to the time that the idea is realized in a real product. But 10 to 20 years seems to be the sort of timeline, right? You can actually see this. So this is an extremely influential paper. In fact, if you think about bounds checking, fat pointers are the key idea that come into play. And as I said in the first class, what you should take away from this course is probably a toolbox of techniques, where if you're told a problem or you encounter a problem in the field, you might not remember all of the details, but the correct keyword must come into your minds. 20 years down the line, 30 years down the line, after you finish your degrees and go from here. And this is a key idea, a key correlation that you should keep in your mind. Bounds checking means fat pointers, right? That's the way you go. And of course, the devil is the details, and that's what we'll be looking at now. Okay, so the project goal over here is to make C and C++ safe and secure. And I already told you what that means. It means introducing Java-like memory safety checks into C and C++. Okay, so the lack of memory safety is the root cause of serious bugs and security vulnerabilities. We already saw that. So let us see how to fix this. And we will start with enforcing memory safety. We will start with enforcing spatial memory safety. And for that, let me introduce you one example. I'll show you a spatial problem. You've already seen this, but the reason I'm showing it is because the same thing will be carried over as the running example. Okay, so here is the bounds violation example, which is a spatial safety violation. So here you have a structure. It's a bank account with an account ID, which is a character array of size 3 and an int balance. Okay, here it's not going to be a buffer overflow in the traditional sense of a stir copy or anything, but you will notice that if I write into this account ID more than 3 bytes, it's going to go and overwrite the balance, which is a situation we would like to avoid. Okay, so here is a program that is going and doing something, and there is no library function, stir copy or anything, but you will see that pointer arithmetic is going to be the culprit over here. So b.balance equal to 0, char pointer is equal to the address of b.account ID, and now I do char pointer equal to ptr, right? And then I'm doing in a do while loop. I'm just writing into this account ID field, and I'm writing whatever I read from the command line, read character from the command line, and then write it. Okay, so you can see over here that there are cases in which if the read character does not terminate and you keep reading more and more characters, you can overwrite the bank balance, and that's what is shown over here, right? So this is a layout of memory. You've got memory and registers, right? You can just single step through the code, right? You've laid out your 3 bytes for account ID and the balance, which is 4 bytes long. Now balance equal to 0, I set it, and character pointer is equal to account ID. So what does character pointer equal to account ID do? Well, typically what happens is that you allocate a register in the machine code for each pointer, and so, or in this particular case, I'm storing it in memory, and when I load that pointer into memory, it will get into a register. You will see that it goes there. So pointer is now pointing to this hexadecimal address 10, and I am loading character pointer p equal to ptr. So now p points to that location, and within this loop I can just keep writing, and I can overwrite the balance field. And this is a violation of spatial memory safety because I wrote more into that character array than I allocated space for. Okay, it's a spatial memory violation. Now, in the last class, I alluded to temporal memory violations, and I gave you sort of a hint as to what these things are in the heap. Let me go give you a concrete example now of a temporal memory violation. Okay, so let's move forward. So temporal memory violations are use after free bugs, also go by the name of dangling pointers. Okay, so here it is, right? Struct bank account PQ, and then Q equal to malloc. What happens is that now I've allocated something which is of the size bank account, so it gets allocated in blue shown in the slide. Okay, so Q equal to malloc. Now I'm taking the address of Q in R, right? So R now holds the same address as Q, so it points to that structure, and then I do a free of Q. Okay, so when I do a free of Q, it invokes the memory allocator, and the memory allocator just goes and reclaims that memory block over there, and it's no longer supposed to be valid memory. Okay, and later on, let's say I do P, but you will notice that R continues to point to that same location. Okay, that memory has been reclaimed. It's not there anymore in the program's address space, but R is still pointing to it. Okay. Now let's say I do a P equal to malloc 10 times size of bank account. Okay, and the memory allocator just so happens to give some memory in that region, which just so happens to overlap where with the location where Q was originally pointing. Okay, now you can see what will happen if I have a statement of this sort, star R equal to something later on in the program. Okay, so what will happen is that if I do a write at this point with star R equal to something, I will end up overwriting the contents of this structure, which is pointed to by P, but this R, the write by R, is not a valid write because at this point I have freed the memory that R and Q both point to. Okay, so that memory which I freed manually over here by this free Q, I did not observe that there was a dangling reference to it, R, which was later used, and this free Q leads to use after free problem. In this case, I'm using the pointer, I'm using the memory location over here after freeing it, so that's why it goes by the name use after free. Okay, so you can see how it causes a memory safety problem, and this is a temporal memory safety problem because it's a problem that happens as the program progresses, right? There is no spatial violation over here, rather there's a temporal violation, a violation that happens across time. Okay, because I reused a pointer that was free. By the way, let me quickly stop here and ask you, how does Java prevent such dangling pointer violations from happening? Spatial we know, right? I mean, it does the base bounds checking. How does Java prevent this from happening? Can anybody tell me?
Sir, is it related to garbage collection?
Exactly, right? I mean, it's related to garbage collection in the sense that in Java, there is no concept of free, right? There is automatic memory management in Java because the Java virtual machine does garbage collection, right? And it will not even garbage collect Q if it finds that there is a dangling, that there is a future reference to this, to that memory location somewhere else later in the program. So it will not even garbage collect Q because there is an active reference to that memory location, which is pointed to by R. And these things are typically done using what are called reference counting. That's one implementation of a garbage collector where you keep track of how many pointers are pointing to a current location. As long as that is non-zero, you never claim that location. Okay, so Java does not even suffer from this problem because it uses garbage collection for memory management. Of course, that suffers from other problems, which is it suffers from memory leaks and so on, where if you have a pointer forever, memory just keeps growing and your program exhausts memory. That's a different issue, but it at least does not suffer from dangling pointer problems. So I'm going to show you unified architecture, that software architecture that prevents both dangling pointers as well as bounce checking using the same fat pointers approach. Okay, the same fat pointers approach is going to solve both problems in one go, although using slightly different ideas. So, okay, so all right. So in the previous slide over here, sorry, in this slide as well as the previous slide, we had pointers over here that were a fixed size, right? I mean, the character pointer over here, this array was of size 3, and this bank account pointer, I know exactly, when P points to a struct bank account, I know how many bytes corresponding to this P I can actually reference as a valid memory location. It is the size of bank account, right? And over here, P, the valid size that I can reference is 10 times size of bank account. But what can I say about things like void pointers, right? Void pointers are pointers that are just 4-byte values into memory. How can I sort of think about a size for a void pointer? And this is something that we will have to confront because void pointers are pervasive in C. Okay, and we will see how we deal with void pointers and how we pass metadata to it. Because there's no way I can initialize a void pointer without knowing what type it points to, right? I mean, I can always assign a pointer to a void pointer of any 4-byte value, but I do not know what size of the memory block it points to and what's the valid size of the memory block it points to. So I have to figure that out. So this solution, whatever I propose, has got to figure that out, and let's see how it proceeds. Okay, so I'll now tell you how spatial memory safety is enforced using fat pointers. And as I said, this solution is rather old, right? These are names of various papers that you will also find referenced in the softbound paper that implemented this idea of a pointer-based checking. Okay, so let's see how it works. The idea is that along with every pointer, you maintain metadata, and this is exactly what I showed you, right? You can make every pointer a struct, and you keep track of the base as well as the bounds. And every time you load the pointer into a register, you also carry over the metadata that the pointer points to. Okay, so each pointer has a view of the memory that it can access, and anytime you sort of extend you perform a dereference and you write into it, you also check the base and the bound. So let's see that in action. So I'm going to maintain together with the pointer the base as well as the bound, which shows over here the 3 bytes that this pointer can point to. So anytime I perform a write, okay, and this is the only time I perform the check. Anytime I perform a write over here, character pointer is equal to something, and I'm writing into this pointer. What do? Well, oh no, sorry. That's not true. Okay, so this over here, actually, I'm initializing the base and the bounds because the first time the pointer is being initialized. I actually initialize the base and the bounds using the statement over here because I know exactly what the base and the bounds are. And when I copy it into this P, I'm copying it to one of the registers. So now I have to copy the base and the bounds also into the corresponding registers. Okay, so the base and the bounds now point to the corresponding location. Now let's see what happens when I actually try to write into this pointer P. So within this loop, what happens is that every time I perform a star P equal to CH, I'm going to check whether this P is pointing between the base and the bounds. Is P greater than base and is P less than bounds? And if that is the case, only then does the actual write proceed. And how do I implement this? Well, I implement this in assembly because the star P equal to CH will correspond to a store instruction either into memory or in a register in this particular case of the value that I want to write. And whenever I'm writing, I can check that the value that this register points to is between the base and the bounds. Okay, so anytime I exceed the base either negatively or I exceed the bounds on the right hand side, as you can see over here, the code, the instrumentation. So by the way, the additional code that I insert into a program that performs these kinds of checks, for example, the canary check that was done when we spoke about the stack canaries, the one that checks the value of the canary and then looks for mismatch. Such code is called instrumentation. Okay, and over here the particular instrumentation that I'm adding will be together with every store instruction. There are a few other places of instrumentation that will become clear, but over here you certainly need instrumentation at every memory write or a memory store. And the instrumentation's goal over here is to check whether the pointer is between the base and the bounds, and if it's violated, immediately I stop the program by throwing an exception. Okay, so that's the idea here, right? So I need registers as well as memory. I need base and bound storage, and so here is one easy way to do it, right? Which is, with every pointer, I sort of associate a hash table, so the pointer can go and point into the corresponding entry of the hash table, and I am able to go and fetch the base and the bounds. So that allows me to implement base bounds checking without having to change the representation of the pointer in memory. In this particular case, the base and the bounds are associated with a pointer in a continuous structure. But as I showed you in the first slide, if you do that, you're changing the representation of a pointer. From a normal pointer, it becomes a structure, and that can be bad with respect to compatibility. So how do you preserve compatibility? Well, one way to do it is for every pointer, you sort of store the base and the bounds in a separate hash table. And then what you do is whenever you're dereferencing the pointer, you go look up the corresponding entry in the hash table by hashing the value of the pointer that fetches you the base and the bounds. Of course, you'll have to deal with hash table collisions and so on, which are standard tricks. Okay, fetch the base and the bound and then perform the check. Okay, easy approach. And there are fast hash functions that are available. The only problem is that this takes around 9 x86 instructions. Now, for every store, what this means is that you have to insert 9 x86 instructions before the store. That can add significant overhead. So there is a better way to do this, which is that instead of having a hash table, you can store your base and bound somewhere else, and this particular paper calls it a shadow space, where you using a pointer, you are able to uniquely index into this shadow space, and you're able to find the base and the bounds. And they show a particular implementation in the paper where you can actually fetch the base and the bounds using 5 x86 instructions, which is better than the previous one. So it's an implementation detail, but it allows you to fetch the base and the bounds in a more efficient fashion. Okay, so let's look at what these checks should be. So every time you dereference a pointer, you perform a check. Okay, so you're going to check whether p is less than p base. If p is less than p base, abort, or p plus the size is greater than p bound, you abort. Okay, so in other words, in this particular case, you just have to check whether p is between the base and the bounds. Okay, so all right, so I think I will not discuss this point. The reason this point is mentioned over here is because in Java over the years there's been a lot of work on eliminating unwanted bounds checks, because they can be a performance problem, but I'm not going to talk about that over here, and neither is it a focus area for this paper. They just focus on getting the instrumentation correct. Okay, so all right, so here is how you store the pointers, right? So whenever you create a pointer, you have to initialize the base and the bounds. And the way you do it is that for a malloc, right, which is a memory allocator function, you identify the memory allocator functions, and whenever you have a memory allocation event, you initialize the base and the bounds. In this particular case, base is p and bounds is p plus size, which is this particular parameter. So you have to hard code this stuff, right? Because there are so many different kinds of allocator. There's malloc, there's cmalloc, there's kmalloc, different allocator functions. But for each one of these allocator functions, you have to sort of initialize the corresponding base and the bounds. Same thing over here for stack-based initialization, right? So I've got an int array 100, and I'm taking the address of that array. The minute I do that, even though it is a stack-based array, I know what the size is. I can initialize the base and the bounds to be p and p plus size of array. Okay, so this is what you do whenever a pointer is created, and whenever the pointer is copied. Right? I mean, let's say you created a pointer like this, as shown in the previous slide, and you do, let's say, another statement q equal to p. Okay, so if you say q equal to p, whatever metadata P has must be copied into Q. Okay, so that's what you do. So whenever you have a pointer assignment and a cast is just a different kind of pointer assignment, you just propagate the base and the bounds. That's all you need to do. When you're copying the value of the pointer, copy the value of the base and the bounds also. Okay. And whenever you load or store a pointer from memory, you load the base and the bound information from this metadata space that I spoke about. And you check, right? Whenever you are dereferencing the pointer, you check. And this is loading or storing a pointer from memory. You also load or store the corresponding base and bound information. Okay, so whenever you're passing arguments to a function, right, you're passing, let's say, a character pointer P, you change implicitly the function definition by passing some hidden parameters, right? So the hidden parameters are now going to be the base and the bounds. So you rewrite the function prototype. Again, this is done automatically. It's not done manually. It's done by the compiler. You rewrite the function prototype and you make it, an underscore f with these hidden parameters passed. So instead of calling f, you end up calling underscore f, and every time you pass the pointer, now you also pass the base and the bounds. Okay, so that's the way you go about doing it, except you can't do it for all functions. So for example, if you've got stir copy, which is a library function whose implementation you don't control, you can't do this, and we will come and talk about that later on, right, in this presentation. Okay, so I'm now going to tell you one of the dilemmas that one faces when implementing this simple algorithm that I spoke about. So take a look at this structure that we have already seen, and I'm going to do something over here. A char pointer ID equal to ampersand of PTR arrow account ID. So now can you tell me, for this ID pointer, what the base and the bound should be? Quick poll. Right. What do you think the base should be? Well, the base is clear. The base is the address of the first element of this account ID. What should the bounds be?
Size of the field.
What's that?
Size of the field.
Size of the account ID.
The account ID field.
Well, you know what? Why? I mean, why can't it be 7? Why can't it be 3 plus 4 bytes? 7, because it's all valid memory, right? Because it's all valid memory that belongs to this structure. And in some sense over here, this ID is just pointing to the beginning of the structure. So what tells you that this is a pointer to the account ID and not to the entire structure? Because the pointer is pointing to the beginning of the structure.
Sir, if I may ask something.
Yes, please do.
Actual memory is not being allocated here, if I am right, because of the C. Because this, we are just saying that the type of the pointer is of this structure. But yeah, we are not saying, we have not mallocked or we have not created any
sorry.
structure.
Okay, so whenever I show code like this, okay, there is a malloc. Assume there's a malloc in between. You're absolutely right, right? I've done a malloc, let's say.
Okay.
So there is actual space allocated in memory. Sorry, I've not shown that.
And PTR is pointing to that object, if I'm right.
PTR is pointing to that object, yes. So PTR is a pointer to that struct, right?
Correct.
And struct arrow, so this PTR arrow account ID. So if you print out the value of this pointer PTR and you print out the value of this pointer PTR arrow account ID, it will be the same value. It will be the same value because account ID starts at the first byte of the struct.
Yes, sir. But the bounds will not be the same.
Okay, so the bounds will not be the same because there is some internal understanding that you have, because that the first 3 bytes over here correspond to ID and the next 4 bytes correspond to balance. But how is this visible to you? It is visible to you as a C programmer. And that's
because of the
sorry, go ahead.
Because the pointer types are different.
Exactly, right? So the pointer types are different, but you find that C programmers misuse the semantics of pointers all the time, right? So what if instead of a char pointer over here, I had a void pointer? What would I do? If I had a void pointer ID, what would I do?
Okay. So, but that is determined by the RHS, the L value, not by the L value.
That is determined by the RHS, and over here the RHS is pointer arrow account ID, but I see that in the source code. Okay. Yes. Once I look down at machine code, I'm just going to be loading the same address. I'm loading the same address because pointer as well as pointer arrow account ID point to the same location.
Correct.
So, okay. So I'm just showing you a dilemma that happens over here, and there are two interpretations, right? There is one option, which is the base and the bound, which is pointer base and pointer bound, which is 7, or it could be pointer base and pointer base plus 3, which is the size of this account ID. And these are two different implementations, right? The entire structure or the structure of the field, and there is no correct answer here. And the reason there is no correct answer over here is because the semantics of C and CC does not tell you that if you exceed the bounds of this account ID and then write into balance, that is illegal. It's not illegal according to the ANSI semantics. It is allowed, and you will find programmers that write programs that actually initialize a pointer like this and use the same pointer to go and change the balance field. It's perfectly valid according to C. And so based upon whichever implementation you choose, you might either, in this first option, you would allow such programs to work, but you will also expose the balance field to any overrides past this third field of the account ID. So that's a cost you will have to pay. And the second case, you're taking the conservative approach where you're saying that only the 3 fields over here can be modified. The minute I step past 3, it's going to be a problem, but you might end up breaking some programs which use this loose definition, which is permitted according to the ANSI, and you might end up, saying that those programs are invalid, even though they might be taking care to ensure that, the account ID field, there's no explicit buffer overflow. Okay, so you will have to sort of this is just a dilemma that the designer has to solve when designing the system. You can choose either one option. Both are correct according to NCC. It's this that you'll have to come up with whatever you want to choose. All right. So the problem here is that the programmer intent is ambiguous, and your optional string of bounds. Okay, so let's look at temporal safety now, right?
Sir, I have a question.
Yes.
So if this dilemma, would it help if C, just a hypothetical situation, if C were suppose an object-oriented language, then we could just have a bound for every object, sub-object in an object. Would this dilemma be resolved then? Like suppose account ID had, this problem is happening precisely because we don't have the bounds for account ID and balance separately.
No. So this problem is happening. Well, you do know the bounds for account ID and balance separately. The first one is 3 bytes. The next one is 4 bytes. The problem that this dilemma is happening is because when you take a pointer of this sort, the intent is ambiguous. Okay, in the sense that, you took a pointer to this field like this, but according to the ANSI semantics, you are allowed to access everything within that structure as long as you have taken the pointer. Okay. And it's not clear from this statement alone, whether
what exactly are we trying to access.
Exactly, and that is the problem, right? And so you will have to make a call over here of how to insert the bounce checks. Okay, whatever you choose is fine, but you have to be aware of the cost, the pros and the cons.
Yes. Okay. Thank you. Yes, sir.
All right. So now let me tell you how the same idea of metadata can be used to implement temporal safety checks. Okay, we will go back to this program where we had a dangling pointer. Okay, so here is the rough idea of how you would go about preventing temporal safety problems using metadata. So let us say that with every pointer, we also store identifier. Okay, so that's what I've shown over here on the slide. With this pointer over here, I've got an identifier called ID1. Whenever I malloc, right? So this pointer is this identifier is supposed to be unique. Every time a pointer is created, a unique identifier is also created for that pointer, a random number. Okay, so now whenever I do a malloc, let us say that I keep a database of valid identifiers. And now I do R equal to Q. All I need to do is I need to copy the identifier for the corresponding pointer that I copied. So Q has identifier 1. So now R has also got the identifier 1 because I just copied the pointer. And now when I free Q, all I have to do is that I need to remove of course, the free will go and free up the space, but I also need to go and remove the identifier corresponding to Q from the database of valid identifiers. Okay, so now if I do malloc of P, now P is going to get a different identifier, right? Every pointer has a unique identifier. So now P's identifier is number 2, but whenever I dereference R, I go and check whether the corresponding identifier of R appears in this database of valid identifiers. Okay, so in this particular case, the identifier for R is 1, but it does not appear in this database of valid identifiers. Therefore, it's a use after free bug. Okay, very, very simple idea, except the problem here is that how do I maintain this database, right? I mean, it could be a hash table, it could be a linked list or whatever it is, but it's now expensive for me to go and check for every dereference in this database whether there is a hit or not, right? It's a flat database of valid identifiers, and we need to check. I need to search that database to check if this identifier is there. Okay, the best case I can do it with a hash table. In the worst case, I will need to maintain some sort of a data structure, a heap or whatever it is, and it's going to take time. It's not a constant time operation. Okay, so I'm going to show you how to make it constant time by a cleverer representation of the metadata. Okay, and so the idea here is a method called lock and key. So let's see how it works. So for every pointer I'm going to maintain, as I said, instead of this identifier, the identifier is now going to be consisting of 2 parts. It's going to consist of something called a lock and something called a key. The lock is nothing but a pointer to a memory location. Okay, so in this particular case, you can see that the lock is a 4-byte value and it points to this memory location F8, and this F8, this is stored in some metadata location, some shadow space that you can think about, and this key value over here that is stored along with the pointer consists of this value 42. Okay, and you will notice that the value that's written in the lock is also 42. Okay, so what happens is that the invariant is that you sort of treat the pointer as valid only if the memory that is pointed to by this lock, whatever is stored over there, is equal to the key value of the pointer itself. So the q.key should be equal to star of lock.value. Okay, in some sense. And okay, so that is what you do. That's the check that you perform whenever you're dereferencing a pointer. How do you initialize these values, and what do you do when there's a free? Well, whenever you allocate a pointer, what you do is that you set the corresponding location of this lock to the same value as this key, and whenever you are freeing the corresponding pointer, you go and you reset this particular value. Okay, that's it. So and you're going to check that the exception is that if the memory of lock is not equal to key, you have a problem. Okay, and whenever you deallocate, as I said, you just go ahead and set this particular value to 0. Okay, so you will notice that, if okay, now I'll show you the actual bounds example and how this particular approach is able to detect dangling pointer errors. Okay, so this is what happens. This memory is set to 0 whenever there's a deallocation. So let's walk through an example. Okay, so oops. So the example is not really okay. Let's work out the thing over here. So let us go back to this example and see how it works, the previous slide. So in this previous slide, what will have happened is that, okay, so Q over here instead of ID, I would have the lock and the key. So let us say that the lock points to this other memory location and I have the key value equal to 42. Now when I do R equal to Q, the same identifier, the same lock and key are copied over to R. So the lock value will point to the same memory location and the value associated with this pointer will be 42, and this lock value, if you go there, it's still 42. Okay. Now I do a free of Q. What happens when I do a free of Q? Well, that free event over here will go and reset the corresponding value for that that's stored at that location to 0. Okay. And now I do a P equal to malloc. Right, so now that pointer P over here is going to get its own lock and key, and I'm going to set the key value, the lock of value to that key. Doesn't matter what the value is, but when I do this dereference star R, I will check that the lock over here. I will go and check the lock location. I'll check the value. there the value would have been converted to 0 by this free event, which will not match the key value stored with this R, which is 42, therefore resulting in a problem. Okay, so that's how the lock and key approach works to prevent spatial memory problems. Okay. All right.
Sir,
So yes, there's a question.
sir, why we need two values, sir, this lock and key. Sir,
Correct.
can't we just store an address and we can store there a bit like 0 or 1, like we will allow 1 if it is valid and we will allow 0 if it is not invalid.
Yes, that is also allowed. So I'm not sure what you're trying to optimize. You're trying to save on the number of bits required in the representation, you mean?
Yes, sir. That way we will not need the key.
The key, okay, the key value, instead of being a 4-byte value, you want to make it a 1-bit value. Is that right?
Sir, I think we can eliminate the key, sir. Suppose I have lock which stores address of a location, and in that address, if the pointer is valid, I store 1, and if it is invalid, then I store 0. So instead of checking if the memory location of the lock is equal to key or not, I can just check if it is 0 or 1.
Okay, that's a very, very good suggestion, right? And it will allow you to go and prevent this. The reason you don't want to do that is because you don't want to rely on the memory allocator. So what generally happens, and I spoke about this briefly in last class when I spoke about heap-based memory allocators, is that once you do a free and a malloc, there is no guarantee about what memory you will get, right? So memory is managed as pools, and the memory that you just freed, you may get as the memory returned to you back on the next malloc. Okay, so you might, so just to take an example, right? So let us say that this program over here, instead of the struct bar, I had a struct foo. Okay, so there is no guarantee that this struct foo, this malloc request, is going to give you a different location in memory, because this free has happened. This malloc has returned this, the memory allocated by this malloc has been returned by this free, and this next malloc could return the same memory chunk. Okay, it all depends upon the memory allocator. Now, if I were to follow your approach, the memory bit would be set to 1 over here. It will be set to 0. It will be set to 1 over here once again. Okay. And so this star R equal to something will proceed, and it will end up corrupting the memory. Okay, just a single bit does not suffice. You actually need some randomness, and that is what is given to you by this key, which is a 4-byte value that is not just a 0 or a 1. Okay, so it is a different value than a 0 and a 1. You see why, right? Because this free would have changed it back to 0, and this malloc will convert it back to 1. And now the R will think that it's a valid memory location. Okay, and the use after free will succeed. Does that answer your question?
Yes, sir, definitely.
Okay, so that's why you don't want such a simplistic approach. Although if your memory allocator, you have a guarantee that the malloc is going to return from a fresh location, your approach will work just fine. But you don't want to make such assumptions, right? And it is well known that memory allocators, especially those that maintain slabs of memory and then try to return the same memory to avoid fragmentation, they end up reusing memory blocks that have already been allocated. So you don't want that. You want to be able to preserve this. You want to be able to actually determine that the memory is stale using the randomness provided by the key value. Okay. Okay. That answers that question. Yeah. Okay. We were here. Okay. Okay, so now the question is, where do you maintain this metadata? So the memory layout you don't want to change, because if you change the memory layout, the compatibility of libraries is lost. Because supposing you have a structure that has a pointer as a field, then what happens is that now you have to change the layout of that structure. Right? You really don't want to do that. You want to preserve your metadata somewhere else, so that the structure that has a pointer field as a member can still remain with the same type definition. Okay, and if you have arbitrary typecast, your comprehensiveness is lost, in the sense that you will not know how to propagate metadata values and so on. Okay, so you maintain a separate metadata region, and as long as you have a unique way of indexing it in that metadata region using the value of the pointer, you can go and fetch the metadata now. Okay, so let's look at disjoint metadata over here, and how you deal with things like casts. Okay, so you have two fields over. You have got two structures over here, a struct foo and a struct bar. And let us say that size t is just 4 bytes. Okay, so both these structures have the same size. As you can see over here, one is an int star and a size b. This is also 8 bytes long. This is also 8 bytes long. So now let us say that I do something like this: q equal to struct bar pointer of p. Perfectly allowed in C. In C, there is nothing more associated with the semantics of a pointer other than the fact that it's a 4-byte value, and all of these things are allowed, right? So if you do star q equal to something, it is also the write is going to proceed, except that the write will happen into the P structure rather than the Q structure. Okay, so now if you maintain your metadata together with the structure itself, you're going to have a problem because the array is going to have metadata. B is probably not going to have metadata, and over here B does not have metadata at all, right? The size T structure is not a pointer. It's not going to have metadata. So if you have things like casts of this sort and you maintain metadata together with a pointer, it ends up breaking existing programs that work. Whereas if you store your metadata off on the side, right, you can still propagate metadata. And the key insight over here that enables things to work is that casts can only manufacture pointers but not metadata. Okay, why is that, right? So when you cast something like this, you're not creating any new space in memory. Rather, you're creating a pointer q and making it assign. You're assigning the value of q to the value of this pointer p. What that means is that whatever metadata is associated with this pointer p can simply be blindly copied into this pointer q. Same base and bounds of p can be copied over to q. You're not actually allocating any new structure. So that is how you can initialize the values of the base and the bounds for this queue with casts also. So that's the key insight over here that allows you to sort of with disjoint metadata still work with this notion of propagation of metadata and pointers with casts also. It programs with casts. Okay, so a little bit of discussion about how you access this metadata space, and here, in fact, there's a detailed discussion in the paper of the data structure they use, and you will see that again it's a trie data structure. Okay, okay. So you use the address of the pointer rather than what the pointer points to. That's how you load the metadata. Let me just very briefly, quickly go over the data structure they use. And if you go and read the paper and look at the metadata that they use, the structure that they use to go and identify where the metadata space, the metadata for a particular pointer is, you will the idea over here will take you back to the concepts in operating systems. Right? In operating systems, whenever you want to do a page, you want to look up the page table. A virtual address is broken up into two parts, right? It's broken up into an offset as well as a page number, and then you combine them together to find the location of the page table where the virtual to physical address translation is stored. You will find in the paper that pretty much they adopt the same idea. There is a root of this trie, and then they take an address and split it into two parts and use the first one to identify the chunk of the trie where the corresponding metadata mapping is stored, and an offset which is combined with this translation will give you exactly where the base, bound, key and the lock for a pointer are stored. Okay, so this is very much implementation specific. I would ask you to actually go and read the paper, and they're able to do this using around 12 x86 instructions for all 4 metadata values. Remember, now you want not just temporal safety or spatial safety, you want temporal and spatial safety, which means that in every pointer dereference, you're going to check for the base and the bounds, and you're going to check for the lock and the key. So whenever you do a dereference, you want to make sure it's within bounds and that it is a live data reference. It's not a use after free. Okay, so it's obviously going to take you more checks rather than just the 5 or the 6 checks that I spoke about before for base and bounds. Okay, so let's see. So here's a design choice, and it is probably okay. I will just talk about it very briefly. Okay, so the design choice over here is that this is a rather esoteric issue that will come into that you will start noticing when you read the paper. So in C, a pointer is not really any sort of special value. It is just a 4-byte value. And what are integers? Integers are also 4-byte values. Okay, and you will find that there are umpteen examples in the real world where pointers are treated as integers and integers are cast back to pointers. Okay, so all of this is legal according to the ANSI standard. I can treat a pointer as an integer, I can store it in an integer variable, do pointer arithmetic on it as an integer, cast it back to a pointer and then use it as a dereference for the pointer also. This is all valid. The only problem is that now if you want to protect such programs also, you have to propagate metadata values. Whenever the pointer is cast to an integer, now you'll have to store metadata along with an integer. And every time an integer is manipulated, you have to also check the metadata values, potentially assuming that this integer is a pointer, even though it might not be, right? So this will throw an unacceptable performance overhead if you are now going to have to maintain metadata together with every integer variable, because integers are pervasive in C programs. Okay, so this is a performance design choice that this particular system made, which is that metadata is only going to be stored with pointers, and that pointers you're not going to store metadata with integers, and this might end up breaking programs that actually cast pointers into integers and then perform pointer arithmetic with integers. Okay, so casting an integer to a pointer is disallowed, and that's a particular design choice that this paper made, and so it might end up breaking programs that do this, but it's a trade-off that this paper made, right? It's similar to the other trade-off that I spoke about before, that struct field and the three the 3 bytes for the account ID and so on. It's a very similar sort of trade-off. Okay. So let me sort of summarize over here the pointer metadata allocation and propagation, right? So whenever I allocate memory, I initialize the base and the bounds like this, and I call a function to allocate a random number for the key, and then I allocate space for the lock, and I store the key in that lock location. And whenever I do something like pointer arithmetic p equal to q plus 10, what do? Well, I just copy the metadata from q into p, right? That's it. P base same as Q base, P bound is same as Q bound, lock and key are just copied. All right. And memory deallocation event, what do? Well, the only thing I need to take care of is the lock and key, right? So I check for double freeze, and then I check that I set the lock star P of lock equal to invalid key, which is 0 or whatever, right? And then whenever I do a dereference, of course, I have to check for base, bounds, lock and key, and those checks I've already described. Okay, so here is the overall summary of how things look like. So you have split up your metadata, and now you're storing your metadata somewhere else in memory, right? It's a shadow region in memory where I'm storing metadata, probably on the heap, organized as a trie. And every time there is a pointer, it has a corresponding metadata in memory somewhere. So P has metadata here, Q has metadata here, and in memory I've got some other location where I'm storing the values of all of these locks. Okay, so bounds check is now easy once you have the base and the bounds, and temporal check also so all you do is that you dereference this memory location and check that this value is the same as this value. That's it. Okay. Okay, so the memory layout is intact and it's allocated on demand. Okay, it hurts locality because now you have to make non-local references, so it might, based upon the cache performance characteristics, your program, the performance might end up getting hurt because now you're accessing non-local things in the program's address space. Okay, so how to go about performing this checking, how to implement this checking? There are many ways, right? One is source to source translation. At the end of the day, right? I mean, I have shown you how these pointers are implemented. I can also take a program that will take a C program and then rewrite it into another C program where I insert all of these checks and then compile it with an off-the-shelf compiler, right? That is one way to do it. Although it is not entirely straightforward, it might not catch all cases. So this particular way of this paper describes a compiler instrumentation approach where you work with the intermediate representation of the compiler that's emitted by the compiler and go add your instrumentation to the intermediate representation. Okay, and in particular, the compiler that they used over here is LLVM. LLVM has now become almost the industry standard. It's become the de facto compiler. It's it's overtaken GCC. It's in very popular use within Google and Apple and so on. So LLVM is a compiler infrastructure that emits an intermediate representation called LLVM IR, on which you can keep performing various transformations, and there are backends that work with LLVM IR to split machine code. Okay, so all of these transformations are implemented within the LLVM IR. Okay, you can also do binary instrumentation, which is that even if you don't have LLVM IR, if you just have a binary of a program, you can directly go and change the binary. The only problem is that if you don't have source code and you just have a binary, it's very difficult to identify pointers, because any 4-byte value can be a pointer. And I already told you, if you are going to be treating any 4-byte value as a pointer, then you have to also treat integers potentially as pointers, and you have to store metadata together with every 4-byte value, which will make your performance extremely slow. So you don't want to go with this approach. You can still do it, but of course you'll have extremely high overhead. So compiler instrumentation, it provides like a very nice middle ground. Of course, it assumes that you have the source code, or that you at least have the LLVM IR of the program that you want to transform. All right, I'll also tell you about a hardware approach that will still work with this with these compiler instrumentation based approach. Okay, so let me show you the LLVM implementation. Again, over here, I will only show the code at a very high level to show you what LLVM IR looks like. For those of you that are taking Udai's course this semester, it must be familiar, because LLVM IR, he's covering MLIR in this course. It's an intermediate representation based on LLVM for machine learning. So LLVM is being used in all domains. Okay, so here is some background on LLVM IR. You can see over here some C source code, right? And what I'm going to show you in the next slide is the LLVM IR, the intermediate representation produced by the LLVM compiler for this particular source code, or at least a snippet of it. Okay, so you can see over here these two pointer stores, fptr next equal to null and new ptr next is equal to pointer, and you'll also see this mallocs. I will show you how they get transformed. So here is the LLVM code for this, right? So you can see that there's a call to this malloc function, and you will see that in fact LLVM IR is explicitly typed. So that means that types that are there in source code, for example, this struct node t and the node pointer over here, they actually get carried over into the LLVM IR. This is unlike machine code, which is untyped. So now you have a node t type that has got two types over here, a 64-bit integer together with a pointer to a node. And so LLVM IR actually carries types down into the intermediate representation. This is very good because a lot of compiler optimizations also make assumptions about the types, or can work better if types are known. So this is carried down into LLVM IR. Okay, so it's explicitly typed. You can see that there is an instruction in the intermediate representation called GEP that allows you to do pointer arithmetic, and you're doing pointer arithmetic over here. And okay, so I'm not really going to talk about what is SSA. It's called static single assignment form, and they have something called phi nodes. We will not concern ourselves with that over here. Maybe I will talk about it when we talk about control flow graphs in the next class or so, but it's not really a critical concept, and it's not important to understand this paper, so we can skip that notion of SSA as well as phi nodes. But what happens over here is that now the soft mount sets will add instrumentation to this intermediate representation, right? So it operates in 3 phases, right? You introduce temporaries for metadata and you populate the phi nodes. Again, phi nodes are not really important here. You can even work without that, and then you introduce the check handlers. Okay, so it's a linear pass over the code, and you are able to insert the instrumentation. The paper has some proofs. The proofs are in a language called Coq. This is actually it's a modern trend. So Cork is a language that allows you to co-develop proofs of correctness together with the implementation of the system. And in the recent years, right, we have been plagued with a number of problems, not just memory error problems, but also correctness problems that have arisen in key software systems. And so the research trend today is to try to make this, is to co-develop your software together with proofs of correctness. And so Cork is a language that is extremely influential that the community is now sort of investigating to build, including big systems, including things like file systems and so on, portions of the entire operating system kernel. They are being developed, verified, because with something like a file system, you want to get guarantees that the file system is not going to lose your data if the disk crashes, right? So you want these proofs of correctness, and things like Cork are able to do this. We are not going to be concerning ourselves with the proof of correctness part of this paper. You're welcome to read it. And if you're interested in this kind of work, I can give you pointers. But you are not going to be responsible for that one particular section of the paper. Everything else, of course, you're going to be responsible for. So the proofs are not going to be part of what at least we will cover in this course. Okay, so where am I with respect to time? I have another 15 minutes, so I can tell you very quickly about Intel MPX. So it so turns out that the person who created Intel MPX is also associated with IISc in a in the following way, right? I already told you in the beginning of the semester that we are broadcasting this course via this Karnataka State Cybersecurity Center of Excellence. And so he is somebody associated with that center. He is leading the startups and industry activity. He is based from Bangalore here. He used to work for Intel for a long time. So he's the person who designed and implemented Intel MPX, and that is now available in all the chips that you use. So given time in the semester, I might invite him to give a little talk about his experiences developing Intel and MPX. Okay, so let's look at the software hardware continuum, right? I mean, whatever I spoke about over here can also be implemented in hardware, and I'm going to tell you how. So softbound does everything in software. So there are zero hardware modifications, but of course the runtime overhead is going to be high. And so what we want is if we can combine software and hardware in some way that reduces overhead. Hardware has the ability to reduce overhead because everything is implemented in silicon. And instead of actually having to execute instructions, these things are hard coded as new instructions in the hardware. And so there is the hope that you can reduce overhead. So let's see how. So there is another system called Watchdog I'm not really going to talk about, but that's the other point in the design space. What I'm going to talk about is this point in the design space over here, which is Intel MPX. Okay, so what does Intel MPX do? Well, to the instruction set architecture or the ISA, it adds new instructions that can perform bounce check and use after free checks, and then also instructions to load and store metadata. Okay, so and you can pack 4 modes of metadata into a single wide register, and then with a single write you can load and store metadata. Okay, so all of these ways you can actually accelerate bounce checking. So here is a concrete implementation. So this is how you would do implementation in software. Before you dereference this pointer q, you would check that q is less than q base. Q is greater than q base and q is less than q bound. If not, you'll abort, and only then you'll perform this check. So this additional code over here, this if then else, is what you added as part of the instrumentation. And so if you were to compile this down into binary, you'll find that there are 5 checks that you can do this in 5 checks for spatial checking. Okay. And with a hardware-based approach, it becomes a single hardware instruction, a new instruction that's introduced called size check.size, and then you pass the register value, and it goes fetches the metadata and then checks it completely within hardware. Okay, so you can as you can see, you can get rid of the 5 instructions and then make it a single instruction check. Okay, all right. So that's the main advantage over here, right? It supports all addressing modes. And it executes as one micro op. Okay, same thing with temporal checks, right? this would be the check for use after free. Instead of, so that's 3 instructions. If you were to do it in software, in hardware, it will be a single instruction that performs the same check, but it's done with a single hardware instruction. Okay, and it's 2 micro-ops and it's latency not. It sort of simplifies the implementation. And as far as the compiler goes, all it will have to do is that whenever there is a p equal to star q, instead of inserting the instrumentation corresponding to all of this, it will just need to insert this instruction over here, right? So that's the software side of the support for the corresponding hardware, right? If you have to use that hardware, the compiler still has to emit the corresponding instructions, and this, as well as the size check instruction, is what it would sort of emit when it's producing the machine code. Okay, so and also for metadata load, typically if you were to do it in software, it's 14 instructions, and the table lookup is 16 instructions to go and look up the metadata. And again, you introduce new instructions called meta load and meta store that are new instructions from the hardware itself, and they work much faster than having to insert 30 instructions. Okay, so that's the hardware software combined approach, where you have new hardware like Intellibx providing instructions like temporal check, spatial check, metadata load, metadata store, and you need compiler support to emit those instructions when you're compiling software so that you're able to get this faster. That's Intellibx. Okay, so how much time do I have? 10 more minutes. I'm not really going to talk in detail about the evaluation, which talks about the runtime performance overhead and so on. Maybe I will just briefly talk about effectiveness in detecting errors. I'd much rather ask you to go and see the evaluation in detail from the slides, from the paper, and do that reading at home. It's very, very instructive when you're reading a paper to understand how performance evaluations are constructed, right? Whenever you build a system, it's also important for you to properly evaluate the system, which means that you have to understand how to design the experiments, what research questions you're trying to evaluate, and how to carefully perform these experiments. You should read the paper. You should not ignore this part of the paper, but I am not going to do a discussion of that over here in the slides. Rather, I'll very briefly talk about how they were able to detect real errors, and I would much rather answer questions or doubts about the system. Okay, so they were, it's not surprising, right? I mean, they took some existing benchmarks that had known memory errors, and they took previously published work that has synthetic attacks. They compiled all of those programs. In this particular case, there were 4 benchmarks that had these known buffer overflows together with the inputs that trigger them, and they go compile it in soft bound sets, and they're able to detect all of the attacks as they happen. Okay, not very surprising, right? I mean, it's a very effective system, and conceptually speaking, at least, there were no holes in the system that allow you to bypass the checks, and so it's able to detect all of these problems, and that's not really a surprise, right? And so there's a discussion in the paper about why previous systems fail. I will leave you to that. Okay, and it also found new bugs, right? So that's good. That's what you expect in any effective system. Okay, so they did perform some source code and compatibility experiments, and there is some more discussion about performance overhead and so on. I will let you read that. And I already told you about Intellibx, right? Even though the instructions that I told you, the spatial check, temporal check, metadata load, and metadata store are not the exact instructions in Intellibx, that's the high level idea. That's what is implemented within Intellibx. So let me stop here and open the floor for questions. Okay, so any questions about this particular approach to memory safety checking? In particular, what I would like you to pay attention to when you go and read this paper at home is compare and contrast in terms of the power of this approach, how it, whether it's able to prevent attacks that other systems are not able to, what are the pros and the cons and so on. Yes, Devraju, you have a question.
Hello,
Please,
sir. Am I audible?
Yes, you are audible.
Sir, like, who are the intended audience for this paper? Like, is it referring to compiler designers or programmers or developers?
The intended
It's
audience
made-
is you. The intended audience is anybody who wishes to take the paper and read it, right? I
No,
mean,
no, no.
I would not. Okay, so I don't
Like,
understand the question then.
No, no, no. Like, with respect to concept discussed in this paper, like, are authors like trying to give some points to programmers or developers who use the language, or to compiler designers or system designers who design the system?
So at the end of the day, it is a compiler-based defense, right? So compiler developers would benefit by taking the concepts over here and applying it to their programs. It also benefits hardware developers because now you can take the same ideas and implement it in hardware. And I think if I understand your question correctly, you're asking me whether this requires any changes on the programmer side. And the answer is no, right? I mean, it works with existing legacy programs as long as you have the source code. There is a catch, however, it does not work with libraries unless the libraries are recompiled. And that's the part that there was one slide that has. Okay, Gokulnath.
So this is more of a design question. So like if C was known.
Sorry, Gokulnath. Gokulnath, just a second. My connection dropped and you have to repeat. I was not able to catch the first part of your question.
Am I audible right now, sir?
Yes, you're audible.
So my question was the non-implementation of memory safety in C. Was it a design choice or were there any constraints that led to not it being inbuilt in the language itself?
That's a good question, and I don't have the historical context to be able to tell you why the design choice was that way. You know, at the time that C was designed, which was in the late 70s, you should go and sort of look at the state of computing at that point. At that point, you know, programming and programs were developed using punch cards, and people still used to write assembly language. Okay, so that is the era in which the C programming language came into existence. Of course, there were other programs, programming languages. There was, you know, COBOL and Ada and all of these things, Fortran also. But C came into existence where, you know, programming with assembly was still very much the norm. And so C was leaps and bounds step ahead in terms of how to express programs. Now, why were memory checks not introduced as part of the programming language standard? Your guess is as good as mine, and I think that some of these, you know, these problems in some sense have been rectified with the design of the with Java. Of course, it's not a perfect solution. And that's why, you know, you see to this day development continues. Now we have Rust. Right? Rust is nothing but C with memory checks, where memory checks are inserted by the programmer, and it enforces a certain discipline using the type system. So I don't have a good answer to your question. I don't have the historical context.
So, sir, on the topic of Rust, since it ensures memory safety as well, is it less efficient than C compared to on some benchmarks?
It is no. So it is just as well. So okay. So I don't know the exact answer to be able to give you a numerical comparison. So the idea is that Rust performs static checks. Okay, there are no runtime checks inserted into the program. It's the compiler's job to make sure that pointers are used in the correct way, and so everything happens statically. And so once you compile, the hope is that the program is going to be secure. Because the compiler passed it. That said, Rust also allows you to insert unsafe code, but you as a programmer have to explicitly insert unsafe code into what are called unsafe blocks. So you are taking responsibility for that unsafe code. Okay, if you want to violate the semantics of pointers, you have to explicitly ask for permission and do it within declared code blocks called unsafe blocks. And it lets you, you know, violate memory safety within those unsafe blocks. But for everything else, it assumes safety as the default and the compiler performs the check. So it's a static approach. So at runtime, you don't see any additional overhead as compared to C. So that's the major advantage for Rust. And the other advantage of Rust is that unlike Java, it's a low-level programming language that allows you control over memory allocation and deallocation. So people have written operating system kernels in Rust, okay, which you cannot do, or which is extremely challenging to do in Java without at least some low-level control over memory.
Okay, thank you, sir.
Yeah. Okay, any more questions? Gaurish.
Sir, whatever we saw today, sir, I guess that was all runtime check.
That was
Because
all
sir, we
what?
were storing, sir, whatever we saw today, sir, that metadata storing and everything, sir, that was runtime check. If
Runtime
I'm
check,
correct.
yes. Correct.
So, sir, how
So
can
you
Rust
have
do
overheads.
that in static, in compile time? Like if it has to store metadata, then it has to do runtime check.
The metadata is checked when the pointer is dereferenced at runtime. Correct. So it is a runtime check, but the instructions, the instrumentation are added by the compiler at compile time. So you're inserting additional instructions that get executed at runtime.
So, sir, how can Rust do it like without any overhead in runtime?
Because Rust requires you to rewrite the programs. The source programs are rewritten in the Rust programming language, and they require you to adhere to a particular programming discipline, and that's enforced using the type system, right? So if your program compiles using the Rust type system, it means that your program is safe by default. So things like casts and so on are not allowed, right? So it will not work with legacy programs. You have to rewrite the program, and that's what the whole exercise behind the project is, right? Which is to take existing programs and then to see what you have to do to rewrite it to make it safe so that it passes through the Rust type system. So Rust is not going to work with legacy programs.
Okay, sir.
Okay. Okay. I think we are past time anyway, so let me just call it a day today. And